Hi, welcome back to AP Physics C Mechanics. All right, so we have two more videos to do here in Unit 2, and this is going to be a little bit more of the challenging one. So this is going to be definitely a newer topic if you've taken AP Physics 1 or an algebra-based physics course, because this is where we're going to be heavily involved with calculus. Did a little bit of a preview when we did that forces and free body diagrams video with the skier on an incline. Because typically when it comes to free response questions, what they'll do is, part A will be draw a free body diagram. Part B will be write, but don't solve the differential equation for it. Part C would be terminal velocity. And then part D is now applying these resistive forces and determining, what is the velocity as a function of time. Okay. So a resistive force is defined as a velocity-dependent force in the opposite direction of an object's velocity. And so F sub S, or not SP, that's spring, not SP, sorry. So it's going to be F sub R for resistive force. Typically it's negative kV or negative BV, but sometimes you may see it as a squared, right? Where that K and B are going to be the what's known as the drag coefficient, and then you can and then you can determine all kinds of things from that. They don't dive in the AP test. They don't dive so much into what does K, what does B equal. It's just a constant value that's attached to it. Okay. So when they ask the question about writing the differential, well, the differential portion is going to come from the acceleration, right? Because you're going to know that you're going to have the sum of the net force, right, is going to be equal to m times a. Well, a is a derivative, okay, dv dt. And then what you would have to do is, because notice it's velocity-dependent force, so what you would have to do is then solve, right, do some separation of variables and get v to one side, all your v's and all your t's to one side, okay? And then what they are going to ask you to do is find, part C will be find the terminal velocity. Well, terminal velocity occurs when the accelerations, right, or the forces and then the m times a, right, the net force, are going to equal each other. So what does that mean? Typically, if it's an object falling, then your acceleration caused by your overall acceleration is going to be equal to the 9.8 number, okay? Or if it's just anything, it's going to be whatever the accelerations are going to equal each other, okay? So if you were to draw a free body diagram of an object in free fall, or not free fall, but experiencing resistive force, right, it would look something like this. Fg down, Fr up. And so you would have Fr equals Fg, okay? And then you solve it out, right? It wouldn't be Fr equals Fg. It would be, and sometimes with these problems, they actually tell you to put Fg positive. So it'd be Fg minus Fr equals Ma. And then you would have the dv dt there. So this would be like your part B, what I just wrote there, Fg minus Fr equals m dv dt. That is a differential because the dv dt exists in that equation. So what happens is at terminal velocity, this becomes 0, okay? So Fg minus Fr is equal to 0, right? So they're equal to each other. And then you just go about solving it, okay? So let's look at an example problem. So this is going to be a little bit involved, okay? So just beware. So here we go. We have an object of mass m shown dropped from rest near the Earth's surface, experiencing a resistive force of kv, where v is the speed of the object and k is a constant. Derive an expression for the velocity of the object at any point in time. Assume that the direction of the gravitational force is positive. So they already give us the free body diagram, okay? So now we just have to sum the forces, All right, sorry, it's not equal to 0. We're not talking about the terminal velocity. Okay, so it's going to be equal to m times a. I don't know why I wrote a subscript a. And so we would have mg minus kv equals ma. So this would be part A. Part B is what we're working towards, which is the differential. So here is your differential, right? So this would be your part B answer. Now they don't ask for it, but part C would be your terminal velocity. So that's where mg minus kv would equal 0, and we call this vt. And so we solve it, and you end up with vt equals mg over k, right? So that would be our expression for terminal velocity. Keep that in mind because it may show up later. And then part D is now to find the velocity at any point in time, the question that we were asked here, okay? So we have mg minus kv equals m dv dt. So I need to get v's to one side, t's to the other. And I can probably divide everything by m if I wanted to, or I can do some simple algebra. So if I divide everything by m, I get g minus kv over m equals dv dt. Okay, so now I multiply dt up, I divide that g minus kv over m over. So I end up with dt, right, equals g minus kv over m, or sorry, that should be dv over, right, g minus kv over m. Now I have to have that in there because, right, it's a minus sign. I can't bring that, kv over m over, and plus I need a variable of integration. So now to get rid of the d's, I take the integral from 0 to t and from 0 to v of t. Okay, and so on the left-hand side, this becomes t. Now on the right-hand side, we've got some work to do here, okay? So basically what happens is if I separate it, I get 1 over g minus kv over m dv, right? That's my integral. So that's you end up with a natural log. So you're going to end up with, so the way it works out is this is k over m is a, right? So the 1 over natural log of a is going to be 1 over a, or sorry, 1 over, call it AV, right? Or A something, AX, right? The integral is going to be 1 over A natural log of AX, okay? So that's what we have to do here. So we're going to have negative M over K, right? Times the natural log of G minus KV over M. And we're going to evaluate that from 0 to V of T. Okay? Now, we go upper limit minus lower limit, so we get ln, right, G minus KV over M minus ln of G. That's it, because if I plug in 0 for V, I get G, ln of G, okay? Now, here's where you get into the idea of like, why do I have to do log properties, right, in Algebra 2? Well, here's why. Because it's applied here in physics. Okay, so I get this natural log. So when I subtract, the first one becomes the numerator, second one becomes the denominator. And so I can do some, some of this, right? Oh, so we kv over m. Okay, so I get natural log of g over g, right? Minus kv over mg. We end up with natural log of 1, all right, minus kv over mg. Okay, so that's what, when I reduce that, what's there in the brackets, that's what I reduce it down to. So negative mk, natural log of 1 minus kv over mg. Okay. Well, now I multiply the negative k over m over, right? So I get negative KT over M equals ln 1 minus KV over mg. Okay, and now to finish my solve, I'm going to do e to the, so e negative KT over M equals 1 minus KV over mg. Right, and so then I need V by itself, so I subtract and add. So I get KV over mg equals 1 minus e to the negative KT over m. And now I multiply by mg over k. And finally, we get V of t equals mg over k times 1 minus e to the negative kt over m. And so I know it's a lot of work here, but basically I have run through exactly a problem that you would have seen on AP Physics C for resistive forces. And notice, you do have to be careful that I'm going to put in something that you shouldn't do on the test, but you may run into, because it's going to say like in terms of mgk, right, constants and so forth. But notice that you have mg over k here, you have mg over k here. So the function can be simplified as the velocity at any time is simply the terminal velocity times 1 minus e to the negative kt over m. Okay. Now, on the AP test, you need to pay attention to what they're looking for, right? So the one on the right in the red box, that would be your AP answer. The one on the left is just kind of like a helpful answer, okay? All right, so we're approaching the last video, which is going to be on circular forces.